And maybe I'll just briefly explain the Milnor fibration and Lefschetz fibration. And let's take an example, which is we have a polynomial for polymorphic. So this is we have n plus 1, so n plus 1 z0 to zn. So this is, for example, L square I from 0 to n minus 1, n plus this at n with n plus 1 or n. That m, I forgot that earlier. But okay, so maybe the n. And then, so we know that there's quick points. So if we want to calculate the gradient, the homomorph gradient, so this will be 2zi plus n so that is quick points is the quick points is at origin, but is non-degenerate because if m is greater than 2, that will be non-degenerate. And so the way to do it, you can like perturb it. You can many ways to perturb it. In fact, I think we introduce this w. So w is another. W will be w0 and wn. This is in another m plus 1 parameter. So you then you perturb it by did I record it? Okay, I record it. And so you perturb that's the last on the polynomial of Zn. And this will be okay. So this, I think, which notation you use? So may I denote HW Zn, and this is polynomial, which is starting with Zn n plus 1, and then maybe I denote W n. Sorry, it's again n plus 1 or m, or maybe it's n. It's n. It's n minus 1. Okay, so or maybe this is plus 1. Otherwise, it will be. Good. Then W1, Zn, and W0. Yeah. So we have, okay. And then you will calculate the gradient. The gradient of the points, the first n, and then the last one will be just the derivatives. That n. So now you can check the critical points. Critical points is 0. So is Z1, so it's just starting with that. So that has to be 0 because, and then also derivative of this is 0. That is critical points. But this implies, if this implies that Okay, so if I take, okay, if I want to look at the equation, so this is, if I look at the inverse of this, so this is points where it is 0, and on this also have another equation because this is this equation, right? And then so what is, okay, so in general, this polynomial, I can write this polynomial for if I fix W, and W is the vector, whatever, so fix this. If I fix this, because it's complex, all complex coefficients, I can always have with multiplicity, there will be have m plus 1 zeros. So I can write, let's look at Zn minus I from 0 to n, right? So that is this AI, the zeros with multiplicity. So okay, so this so if I what this, so this means that n will be these zeros. That is, and also if we take the derivatives, and then if you look at so that will be sum, and this will be j not equal to sum. I from 0 to n. So there will be a chain rule, and each term, then j is not equal to I. Right? So that is that's derivatives. So now if we require this is 0, okay, what you're thinking? Okay, what I'm saying that so if there are if there n maybe it is okay, if that n belong to delta, the delta is a 0 to a n, where there's multiplicity. So that means at least how do we say, at least 2 repeating the list I not equal to j, ai equal to aj. So if we have roots appearing twice, and then Zn is this is like a double multiplicity 2. If you take that roots, then this will be 0 because that is the roots, and then because then this will be also 0 because of this. Okay, so and then maybe I just try to be otherwise. So next is so we want to choose. So like we choose W, which is okay. We can choose W. There's a relation. For example, this W0 will be the product. So there may be a sign, plus or minus. There's a sign of this product AI. So actually, this up to a sign this will be the symmetric polynomial, symmetric because you can just look at coefficients. And so you can choose this W. So choose, let's see. Okay, let's choose W small. So let's choose W small. So maybe I choose the other way. So if because this condition, you can choose W such that choose W in some set such that have no critical points. And then next we can look at this Milnor final, which is ball. We can make it a small ball. So it's 2n plus 2. The origin, both data and this. I think that maybe I can write something and then let's check that. Okay, so this is okay, so we're going to look at so this is our space. So this space will be okay, so going to look at this hours. We could take a okay. We look at this. So this is our space. So this is the Milnor fiber. I mean, here. So Milnor fiber actually in some way is the fiber of this after some perturbation. And now so Milnor fiber. So this is complex manifold of dimension, comfort dimension n. So this with boundary, actually with contact boundary. And then we look at in last time Kim Tin talking about the union, taking union with W. So then you have another vibration over this space, and then that is the fiber. But then we are now I have to look at some disk. So this disk is Z, and try to get Z squared is L plus WZ less than or equal to 1. Some small, this inside unit ball. You see. And then this is Lefschetz vibration. Actually, so this is so this Lefschetz vibration because you have as long as because okay, that's what, for example, if I choose variables, I fix a little W, and then whenever Z, so this ZN, so this is essentially is taking that, of course, the satisfaction, and is it's mapped to Zn. So if you look at equation, the equation is I from 0 to n minus 1 plus hwz. This is 0. Suppose our AI z, so Zn. Suppose Zn is the zeros. Okay, so it's the zeros of this. Say Z. So this will denote about this n plus 1 root. And then this, and also, so if this is 0, if this now this is 0, and this is the holomorphic mass, right? So if Z belongs to this is 0, and then this is a holomorphic Morse function in standard form. So that's why Lefschetz fibration. And that is the only critical points. So all the other, the only the local model. So that is this is because of these two. And then so let's just like we can assume that W is very small. If this is very small, and this can be also very small because they are related by this symmetric polynomial. And then, so let's draw this picture. Let's say I'm going to draw, let's just pretend that this is our n0, n1, and n. So let's choose one point on, which is also joined by line. I draw it as straight line, but it's only an intervals. So good to note this is P0. I think this is location in P0, B1. And then this is Bn. Okay, so now, so these are the critical points. And then look at the, there is, if you look at Lefschetz fibration, right, so now, so I denote this, I say, I think, maybe did Kending denote E?
Which one?
Yeah. So now the total space, so total
E, yeah, E.
E.
Yep.
And then, okay, so here is our W. And then near these points, so there was singular fiber. So if you look at regular points, so here is the regular points. So there's the vanishing sphere. So there is a vanishing sphere. So this is 2m dimensional, 2m dimensional. And this vanishing sphere is in the fiber, generic fiber. And then when you look at, you have like a family of this vanishing sphere. And if you look at the crit points, the vanishing sphere was collapsed to 0. If you look at, so actually this is, remember that this is vanishing sphere of dimension n minus 1. And then over this interval between these two points, if you look at this, they have a sphere, and then it collapsed to a point, so it's a cone. So topologically, this is a ball of dimension n, right? Like a ball of dimension n, and then the radius getting smaller and smaller sphere, and then collapse to a point. So that is another picture of this. And then it going, so that is, so if you look at this side, is the ball. But you also have other side. So then you have other side, and then you have maybe call this is relating to A0. Maybe I denote A0, and then here I have another ball. Okay, maybe it's kind of confusing. Maybe so there's one ball. They call this minus, and this maybe it relate to the pass. Actually, this is something related to the pass. Maybe it's also P1 plus P1. There's another ball. And another ball they glue along the sphere. So that actually again the sphere of n-dimensional. Right? So this is a sphere of n-1 dimensional. The ball of, in fact, that's over this interval. In the whole thing, what we call the Lefschetz symbol. In this case, a Lefschetz symbol is again the sphere. But this sphere, you can check that in this case, it is real, actually Lagrangian. So this is a Lagrangian sphere. Lagrangian sphere, n-dimensional. Okay, so that is, and then you will have you draw this here, and this is sphere, and each you have a sphere. Right, so then you have this is n-1, but the whole thing is Sn. Sn. So you have how many of them? You have m. So each is so you have m many. And then this is for this interval. The Lefschetz symbol gives you the sphere, and you look intersection points. It only intersect each at one point. Okay, I think maybe I spent too much time. So now back to physics.
This is almost what I want to talk about.
You always did. Okay, maybe.
No, I can add on if you want.
Okay, sure. You can.
Yeah, I can add on to this thing.
So maybe did I sharing this? Okay, maybe you can add it on, or maybe do. I thought that maybe I do a quick sharing. Okay, back to you.
Okay. Okay, so yeah, almost the same as Brian, but I add on some terminology. So last time we introduced the definition of Milnor fibration, and today I want to start with this example here. So let's say this is a small dimensional example. So let's say you have a x0 square plus s1 square equals to t for some t. So s1 and s2, s0 and s0 are in C. And you can, this is equivalent to a Riemann surface where you'd view as a double branch at minus t, square root t, and then square root t and minus square root t. And let me draw it properly here so that you can see. So okay, so we can actually see, so I draw a circle here, and this circle surrounding this branch is called a vanishing cycle. It's a generator of homology in this case, where when you view this Riemannian surface as this cylinder here. This is small dimension, so I can draw it in a cylinder way. Okay, and this generator will become a generator here. So this is the vanishing cycle. This is also the zero section, which we will talk about later. where Brian used it to build the sphere just now. So this is also a zero section. This is also a vanishing cycle. In Picard-Lefschetz theory, this is the vanishing cycle. And
Probably zero section means zero
Uh-huh.
section of the cotangent bundle.
yeah, zero section. Yeah.
Because Lagrangian,
Uh-huh.
there's Weinstein-Lagrangian level
Uh-huh.
theorem.
Uh-huh.
So for any Lagrangian, its normal bundle is isomorphic. It's symplectic morphic to cotangent bundle with a canonical symplectic form.
Yeah.
And that's zero section.
Yeah.
Is cotangent bundle identifying the level here.
Yeah, right. Yeah. Later I will write it in a more precise way. Yeah. So the Milnor fiber we talk about is in a higher dimension. So like what Brian said just now, we have this function here. How should I write it? So call it a GW x equal to x1 squared plus. So the from bit here is like the Morse function, okay? And then the last bit we add on is the singularity part. So the singularity part, we do some modification on it, which we call in the Picard-Lefschetz theory, we call it a Morsification or some perturbation, okay? So that the critical point is non-degenerate, okay? It's like how Brian did just now. And then what else? Okay, so now we want to talk about like how, okay, let's say, so okay, tell you a fact first. So this W can be chosen such that HWSN is non-degenerate, and then form this that Brian said just now. And this is where we study the curves, which I talked about last time. Okay, so this curve, okay, so you can imagine this like this. So you imagine this like this. Okay, and then the critical points are the roots of the polynomials. So Brian said you can represent them in terms of these how to write it, W0 up to Wm. Okay, so these are all separate non-degenerates, and then you can actually form path between them. And okay, so first of all, in Picard-Lefschetz theory, they call this kind of path a vanishing path, where you end at one critical point. And Seidel in the book called this kind of path joining two critical points is matching path. Okay, so how are you going to get Lagrangian out of it? So first of all, let's go, let me turn it. So okay, so you look at this familiar inverse image of this polynomial. Okay, in the previous example, we only see up to n equals to 2, but now we see the whole n coming out. And you look at this fiber here. Okay, so this fiber have a property which is, I can draw it here. So at the critical point, I draw a low dimensional picture here. So let me write it out. Let me use different color. So okay, so at this point, the fiber in low dimensional picture is like this. And then for the other point, you'll see something like this. And you can observe that when you get to the middle, the radius will get bigger. Okay. So because like what Brian said, this is like isomorphic to some cotangent bundle, you can consider the zero section. So the zero section is literally this, the middle part here. Okay. So this is the vanishing cycle, but if you identify them as a cotangent bundle, then these are the zero section. Okay. Now for every curve in your disk, you take the zero section and then take their union. So for example, for this curve here, for this particular curve here, you can think of it like you take a point, and then the next one you get some circle, 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 and then become a point. And then you join them together. Maybe I draw a bit bigger. Yeah. So this is the Lagrangian sphere that you can get from the curve in the disk. And this is the Lagrangian submanifold. And then how about the AN configuration here? Is like you take the generator in this disk, which is this curve here, this curve here, this curve here, this curve here, and this curve here. And then you form all the Lagrangian submanifold that formed by these curves. And then you can see that they intersect when they're side by side. They don't intersect when they are far apart. Yeah. Any question?
So the cotangent bundle you wrote
Uh-huh.
a little.
Sorry.
Is the cotangent bundle what? S?
Let me write it properly.
Okay.
Yeah. And you also can identify this with tangent bundle of SM. So you can write out the coordinate. Right. This is equal to UV, and then in the sine, cosine, and then zero, and also this thing is 1. Yeah. Okay. And do you want me to talk about the Taiwan action thing?
Which part one?
Oh, like
What's your
how
plan?
maybe I talk a bit on how the fundamental group of the disk can lift to the symplectomorphism.
Mm-hmm. Yes, that's good.
That's it.
Yeah.
Yeah. Okay. Yeah. So in this case, we obtain an AN configuration, Lagrangian submanifold in this disk, And because now we want to study action on this, so the action on this is studied long ago before. It's like the mapping class group of punctured disk. But now they want to use this to study the symplectomorphism of this Milnor fiber. Okay. So okay, maybe I talk a bit about mapping class group of the punctured disk. So the homology of this disk is generated. Okay, first, if you want to talk about pi 1 of the disk, punctured disk. So punctured disk I put like this, punctured. Okay, so this is punctured, and then if you want to talk about pi 1, you need to pick a base point first, and then form this homology. So you pick orientation. Maybe normally we pick anti-clockwise, I think, and then this homology will form bases for this pi 1 here. Okay, so the mapping class group on pi 1 is just like twisting around the puncture. For example, so I write M mapping class group action on this, also induce action on pi 1 of the star. So if you say you twist this two, so I twist this two around. Okay, I twist this two around. So what picture I get here? So I get a picture like, so let's say I put different color. So this two. So the red one become here, the green one, the blue one becomes on the first one. Okay, and then you can look at how the homology change here. So the homology surrounding this will become like this, and then the other one will become like this. Okay, but you can note that actually you can express this path here using this two path. Okay, this is a bit of algebraic topology. So this is the mapping class group. So okay, so okay, so how about, or any question on this mapping class group stuff? Quite briefly intro. If not, then we go to this symplectomorphism stuff. Okay, so for this symplectomorphism, I just know the construction, but I don't know like how to concretely lift stuff. I know the construction, but I don't know how to lift. So I will say the construction first. So okay, so first of all, last time we introduced this Milnor fibration. Okay, and then you can look at the tangent space of E. This tangent space of E is break into direct sum of two pieces. One is horizontal, one is vertical. Okay, and then this vertical part is actually the kernel of the derivative of pi. And this horizontal part is the main part we want to look at, where it gives the parallel transport. So this horizontal part is what is point such that if you take this should be a two form, I should write a is the connection, okay, maybe I write in this way. So is WP W is the connection form. Is that right, Brian?
Right. What is omega?
Omega is the connection one form.
Or do you need to choose one, or maybe there is?
Need to choose one. Yeah, I think they have some condition that they want to choose, but they say
But
they
if
can always choose one, huh?
if E
Mm-hmm.
E is a symplectic form, which is like a
Mm-hmm. Mm-hmm.
is that sometimes they call the symplectic manifold exact.
Uh-huh.
It
Uh-huh.
has something to do with. So you have this.
Um.
Of course, I mean,
Yep.
once you have a connection,
Mm-hmm.
but this connection.
Yeah. Oh, you
Is,
mean where they get this connection from? Is it?
yeah, the connection.
Oh, yeah. In the paper, they have some condition on finding a two form on this E, and then D is really.
The other way around. D omega is D lit omega.
Sorry.
Okay, so okay, so maybe there is a canonical one. If E, because
Mm-hmm.
E has this exact symplectic form,
E has
because E is coming from
mm-hmm.
Cm plus 1. So
Mm-hmm.
that canonical
Mm-hmm.
symplectic structure is exact.
Mm-hmm.
And this exact, I think you mentioned that last time.
Uh-huh. Yeah. Right.
I think this will be the one connection. The connection one form
Mm-hmm.
is zero. Is that connection one form? Because I mean, it's not a precise connection form. Usually, connection form you have a structure group. Oh, okay. Here the structure group is
Symplectomorphism.
yes, symplectomorphism,
Mm-hmm.
and then the algebra is very big. So maybe it's not quite the strict connection form, but you can use this to find horizontal.
Not strict connection.
But I mean, usually the connection form is the Liaggio value form, even locally.
Yeah.
Here maybe the algebra is like okay, maybe it's just one form, a connection one form. Maybe can make sense of this.
Oh, but actually one place. Okay. You know what? Let me finish this one, then I ask you. So after this, we can define the parallel transport using the horizontal subspace. So this is called horizontal subspace. Subbundle or subspace. And then define parallel transport. Like, and then so the monodromy is like taking, so okay, so monodromy, so monodromy is sorry,
What was capital E here? I haven't seen it.
okay.
Is it arbitrary or is it defined somewhere?
Oh, it's defined last time, so I will
Oh, last week. Right?
This is Milnor fibration.
Is Milnor fibration.
Yep.
Okay.
Yeah. Okay.
It's just a union of the E sub little w. So you have so W is, so
Yeah.
big W is a space when you have these coefficients of this perturbation, multiplication. And when you choose this such that, okay, so it's the union of this.
Yeah, right.
Each fiber is a mirror fiber.
Yeah, each fiber is a mirror fiber, yeah. So, okay, maybe my picture is like this. Okay, draw it. Okay. So, okay, just now we have point here. Right, so let's say we take a closed path here. Okay, so every path here we have fiber on the top. So let's say we draw it. So I'm gonna draw it like this, draw it like this, draw it like this, draw it like this, draw it like this. Okay, and with this decomposition, with this horizontal subspace, you can actually lift this loop up to the fiber so that you get a monodromy group. So this fiber is like EW.
Maybe return to different point or return to the same point. Is this flat?
Okay, if okay, monodromy is like return to the same point. If holonomy, then you can return to different point. Monodromy, you can only have loop lift up. If holonomy, you can lift up path.
So what monodromy is I thought monodromy is holonomy, just a maybe.
I think the difference is one is just have loop, the other one can have any path.
But then what's this monodromy? What is, I mean, when you start take monodromy, you associate a loop downstairs. And then monodromy usually is a diffeomorphism of one particular fiber, is that right?
Yeah. Because So this is a loop, right? Because you come back to yourself.
So then there will be identity. Then monodromy is identity. Well, I think it's returned to different point.
Why is that identity?
Because if you have power transport, if like curvature, you have a curvature. Curvature is not zero, so it's not flat. Even, I mean, usually it don't return to the same point. So I mean, if you look at monodromy, maybe definition. What is monodromy? I mean, we said what is the monodromy exactly?
Are you two talking about different things? I think, Keesing, you're talking about the loop being closed on the base space, and Brian, you're talking about being like not closed up in the fiber.
I get what Brian means.
I think it's just your picture, isn't your picture showing that it's closed up in the fiber?
Okay.
Where it possibly isn't.
Yeah. I think I get. Okay. I get what Brian means. So you get back to the fiber, but you don't get. Maybe you don't
same
get
point.
To the
Yeah. Okay.
Yeah. Right.
So that is.
It is.
Yeah. The main point is the bottom loop is closed or not.
Yes. Yeah.
Yeah.
It'd still be useful to define monodromy. Can you write down the definition of monodromy?
Let me. I didn't. Did I write down something?
Or have we agreed that monodromy is just holonomy over closed paths?
Yeah, I think so. Yeah, I think that's it.
Maybe give a reference on the.
Yeah, I give a reference on the 263. So, yeah. So you can see the definition of holonomy in the Macduff-Salaman book on Introduction to Symplectic Topology, page 263.
Yes, and thanks. I know holonomy. But a moment ago, there seemed to be a difference between them. But
because the confusion is the closed loop in the fiber. Yeah.
In the base space.
Not
Not in the fiber.
Yeah, just in the base space, not in the fiber. Yeah, so Brian, what I don't understand is this part here. Like how you actually lift this thing. Like how you actually do this carrier transform.
You're starting with a point,
Mm-hmm.
and then you have a vector fields on the vector fields along the loop downstairs.
Vector field.
And you're starting with then each point you have a horizontal.
Mm-hmm.
So you try to look at the corresponding horizontal vector fields on each fiber.
Mm-hmm.
There's a there's a unique lift of the tangent to the curve and the base space to the horizontal vector fields on the fiber on the bundle. Yeah. Sorry, Brian.
Yeah, that's correct. That's correct. So,
and then there's a unique ODE solution to solve in the bundle. There's a unique solution to the ODE that the derivative of the path is the horizontal vector you've just lifted.
So maybe restrict the fibration to this base loop on the base space. So that is, you only look at the fibration over this loop.
Mm-hmm.
Then along this loop, you have the tangent vector, right? And then you can lifting this tangent vector along this loop to the horizontal vector fields on this fibration restrict to this loop. So you have vector fields everywhere. When you just draw that, you draw a fibration over the loop, and each point you have vector, you have horizontal vector. So you have vector fields on this whole space, which is fibration over this loop.
Okay.
And then a vector fields, we choose the LA initial points, and you can take an integral curve. You can just solve the ODE. Even usually solving local, I mean, you have a local solution, but because the base is S1 is compact, so the solution globally exists. But the global exists, I mean, vector fields, you have these vector fields, it looks like a cylinder. I mean, if you think on the cylinder, but even the looks like cylinder, but the horizontal tangent vector is not horizontal. So actually, this horizontal tangent, someone call me.
Listen.
Yep.
If you want a reference for like that proof there using those horizontal sum bundles as a definition connection, you can look up section 2.7 of Morgan's book on gauge theory.
Okay.
I think Brian's got the lecture notes somewhere. He talks about that if you want to find that like an actual proof written down. That helps.
Yeah, that's the lemma 2.7.1 in Morgan's notes.
Okay.
So you just solve ODE. So you have like you can maybe in the Dropbox the other special topic like there's a gauge theory, and there you can find the thing. So you can these ODE vector fields. You shall have gamma t, like you have a gamma tilde, like you have a loop. You want to you're lifting a curve, but this curve is not closed anymore because its tangent direction is given by this. You can, for example, suppose your fiber just one-dimensional, and you declare your horizontal lifting is not horizontal. Actually, is an angle, say some pi over 6, some small angle. Each point, because it just you project to the same vector. So you look at a cylinder, and then you choose the horizontal vector fields, just like a horizontal at each point. You have a true horizontal, so that's like a trivial connection. Instead of trivial connection, and you just rotate upwards by fixed angle, say pi over 3. and each point, and then you're working around, maybe you will have this angle. So this will be return different points. So you have a vector field, each vector fields, and you have an integral curve. You try to draw a curve which is tangent direction. So if your horizontal vector fields is not horizontal, actually it's lifted by pi over 3, and the integral curve will be a straight line which is pi over 3. And then we can, because you have a pi over 3 on the cylinder, but the cylinder you return, right? So you can draw it, depending if you're working around, they will probably depend on the angle. So you have you draw a square. You draw a square, then you have instead of horizontal, your integral curve is pi over 3, and then pi over 3, maybe 3 times we return to the same point. You have on a rectangle, you try to draw a straight line passing through the origin, which is a slope, which is pi over 3. Maybe just like the pi over 4, and then diagonal. This is the diagonal. And then you can see that if you build a cylinder, you fold it back, and then diagonal. So then you have a gap. So it will be jump by 1, for example. If you think the cylinder is a straight line, which is vertical, and then S1. Can think S1, which is R modulo Z, and then your connection is pi over 4, and then holonomy will be adding by 1. So that is a monodromy. Monodromy is in a way which is the diffeomorphism of the fiber. But here, here the connection is a bit strange, because the connection is just omega p is just one form. So it's usually the connection is a Lie value one form. Maybe in this case,
well, if it was if you're talking about the principal bundle that E is associated to, then it'll be
okay. So maybe this associated bundle is like is that always the U1? Okay, maybe for the Milnor fibration, the stretch group is U1. Could be. Then if that could be U1, and then you have choose omega, little omega, and then d omega is the curvature. Maybe look likely that's the case. Okay. Yeah, so maybe okay. So you want to continue today, or maybe you want to stop and next time?
Yeah.
Maybe continue next week.
Continue next time.
Yeah. So maybe some. I think maybe okay. Let's go back. I think I share my screen. I think I have some my old notes. Okay, so power transport. I think I have power transport. Maybe something. This is not the fibration. This is a vector bundle. Okay, so very similar. Power transport and holonomy. So here I'm talking about the vector bundle with connection. You can fibration. So you're starting with a principal bundle or maybe a vector bundle. And the connection is given by local connection one form.
Brian,
the Lie value of one form. Yes.
The screen is not shared.
Oh, sorry. Okay, maybe I didn't. Or some other sharing. Maybe the. Okay, so maybe I try to share it and then before you quit. Okay. So here is my other lecture on gauge theory. So it's the parallel transport and hormone group. So it's starting with the principal bundle, or maybe associated vector bundle. But you have a fiber bundle. So maybe that fiber bundle is the associated principal bundle is U1. But let's assume. So the connection won't form. So either is the Liaggio value won't form, or maybe is so if you have a transition function. So usually you have connection won't form, and this connection won't form has, say, on the chart U alpha open state. They have transition function, and then this won't form. Say everything in the matrix valued. So this maybe the algebra is a matrix, and then maybe it is minus or plus minus T alpha T G. So this is G alpha beta is a matrix valued function. So it's a function, the smooth function on the intersection, taking value in the algebra, maybe just in multiple K by K matrix. And then this is the connection form. And then the horizontal lifting, right? So how in the suppose we have, say, yours case, you have a closed curve. Suppose I have some curve on the base.
Yep.
And then this is gamma t. So now I want to have a horizontal lifting of another curve called gamma tilde.
Yep.
The gamma tilde, each point is taking value. So you can think that either you can think that can E restrict to this gamma. So it's a bundle over gamma, and then probably can think this is parameter by t again. So this is a map from the 0, 1 to x. Then you have a tangent vector on the base, and then on each point t here, and you will find st. So st will be horizontal. So this is given by the fiber st. So maybe this is st. This is st.
So the gamma dot t is the
tangent vector on the gamma curve.
Okay.
So this is on the base. Tangent vector on the, because this is like a derivatives in the t direction. So and then the connection, you can take a covariant derivatives. And here is your section, and the connection, you have a tangent vector. So this is a covariant derivatives. So in the parallel, in the same way, which is solve this equation. So here I'm, without talking about the horizontal vector fields, I'm saying that horizontal vector fields is solving this equation. So, and for example, if you take this tangent bundle, and the connection is some, let's just, for example, compatible, remaining metric Lefschetz connection, and then the geodesics is you have some, so geodesics, this will be gamma t, the tangent vector. So okay, so the geodesic, this is because you have, and then this is the tangent vector. The tangent vector is parallel to itself. So that's geodesic. Here I'm talking about the horizontal lifting without mentioning the horizontal vector fields. So I solve this equation. Then you try to solve this equation, there is a connection form, and then there's always a unique solution because
ODE.
this unique solution. You can do, because this is like a ODE. Because if I write in local trivialization, vector fields is just the functions on k-value functions, and this is the tangent vector applied. So tangent vector applied to this function. Then this connection. So I solve this equation. If you look at this side, you just restrict this function to each of curve and then take derivatives. And this is a matrix, k by k matrix. So you can think that this equation is a linear, first order ODE, like a system of you have k variables, and you have partial derivative in T, and this is K by K matrix. So it's the ODE. And usually this you have a unique solution once you have an initial value. So now suppose I have initial value P0 in the fiber, and then solve, you have lifting, then they have a unique solution, and then the limiter, they look at the evaluator at the end, that to give you power transport. That to give you power transport. I think this note in the Dropbox in the other folder, subfolder folder. And then if you have a loop, and then this will be the same fiber. So this will be, I mean, here is everything linear. If a vibration, this is not linear, this will be different morphism. And then here, if you loop, you can do, if you reverse the loop, and then you have identity. So that means actually it is invertible. It's also a group homomorphism. When you have a loop, you have concatenation. You can join the loop, and then the homomy. So homomy in the sense is the same thing as monodromy, if you think. And then there is okay. So here something which is
this horizontal distribution is the horizontal subbundle.
Yes. So now actually here I use this to motivate a definition and a proposition. So a connection, because this is the undergraduate the course. You do the principal bundle and horizontal lifting. So in a way, so now given a connection, we define connection, then we define unique horizontal distribution by solve this unique solution to this ODE. So about ODE, you can solve that. And then this give you a horizontal. So it's like going because that course
different
we're doing differently, doing connection and then define using connection define horizontal, and then this horizontal has this property. Each tangent bundle at the you have a horizontal tangent bundle, tangent space, because then this is the fiber is the vector bundle. Fiber is a vector space. The tangent space of the vertical tangent space, which is tangent to the fiber, is just the same as the vector space. And then in a way which is a decomposition of this exact sequence. Yeah. So and then you can then next theorem is that if you want to there is a curvature, you can calculate curvature out of this by taking two directions, take a lifting. So I calculate to there. And if the curvature is flat, then it doesn't depend on choice. The homomy doesn't depend on choice of the. So if the connection is flat, if it's not flat, then it will depend on the. So, but usually in your case, even though it's not flat, the LA2 pass is a homotopy.
We'll
give. So that means you have a. So usually, if in the case, I think in your case, so you have something which is maybe this is D, maybe the base, maybe it's called base, and then you have a diffeomorphism of the fiber, or maybe it's W. Okay, so and then this will be EW, and then if we have, so this one you have this monodromy, maybe just denote this is the monodromy, and then if this is homotopy, then of course
give the same.
They give you the same path. So this will also homotopy. So like so.
You mean?
So that means you have a path. You have a path connecting. What you call S from 1 to 2. Join them, and then you have family of the homomy or monodromy connecting these. So that means these two monodromy can be joined by a path. So if you want to modulate,
are you saying this is not true in general?
Actually, no, this is always true because
always true. Yeah. Okay.
Because if you want to pass into the homotopy, and then here you also modulo homotopy, like isotopy.
Oh, okay.
So here you modulo homotopy, so that will give you fundamental group. And then
okay,
here
right.
give you mapping class group.
Oh,
so this
okay.
one more like a pi zero, the connect components.
Oh, yeah, yeah. Oh, okay, correct. Yeah.
So this is like
correct.
so these are also homotopy pass connected. And then this will be something what is called the mapping class group. You can think of this different morphism zero. So this will be mapping class group of E. Right? Okay. So maybe you continue on more about that next time. No?
Okay.
So any question, everybody? So maybe you need to just ask everybody, make sure that they understand that the seminar is the way which is a good opportunity to learn, and everybody make sure understand that. Don't ignore that, and then you learn nothing. And that's the purpose of seminar is we have time to discuss, make sure everybody understands that. Okay.
I got one last question.
Yes.
So last time like you define all those flow homology is to compute the pseudo holomorphic curve, right? But seems like in their paper they don't do it in that way. They come up with some symmetric argument and then they just got the number. They don't go through the every.
Usually there's combinatorics. So if in low dimension, I think we did that on the torus, right?
Yeah.
The low dimension, there's no room to move. As soon as you assign boundary condition, and the holomorphic disk, holomorphic triangular is unique.
Oh.
And then depending on how many times you're wrapping around the different homology class or the different energy, different degree, will be counting differently. So in reality, it's very hard to compute to counting harmonic curves. It's always by examples, by look at the combinatorics and see harmonic solutions by counting. I think or maybe by symmetry or by the way which they can count. Yeah. So we will come to that. Look at these examples. Yeah. So next time you will continue on about the
Den twist.
Yeah. Also maybe den twist. So maybe do it on the category. I want to.
Okay.
Suppose now Fukai category is all possible Lagrangian. But suppose we only look at these variations Lagrangian spheres, which is this sphere, but this sphere which joins in this particular way. So AN, so AM type. Suppose you have two Lagrangian, there's only one intersection points. Then of course the chain complex is trivial. There's only one generator.
Okay.
So that is like you have two Lagrangian. They only have one intersection point.
Yeah, right.
And then the chain complex is only one dimensional.
Okay.
And then one dimensional, there's no homology group. So homology group is same as the chain group. But so that the Floyd homology group is also one dimensional.
Okay. Yeah.
So
correct.
in that case, and then but then you need to create more Lagrangian. So we suppose, I think they call the Fukaya Saido category, which is only talking out the Lagrangians. The object is these Lagrangian spheres.
Yeah, correct.
And then apply the den twister, and we apply iterated. Right? You have so many den twister. You have n spheres. Each sphere you have den twister, so you have many den twister.
Yeah,
then den twister, essentially you have generator and also apply den twister.
Yeah,
but den twister form a group. Often in a braid group. Sometimes in your case, it's a braid group. So that means whenever you have braid group is a group element. So it's generated by the den twister or is the inverse.
Yep.
So whenever you have braid element in the braid group, you apply to these Lagrangian spheres. So you can generate many other Lagrangian spheres.
You can make. Okay. Yeah.
So then you have, this will be the Fukaya-sidal category. You look at Lagrangian spheres and obtained by applying the Milnor twister, all possible way. So you can think that we're starting with, which is only AM object. And then the morphism is very simple. Each, if they are adjacent, is one dimensional. If they're not adjacent, then there's no, is zero. So that category is very simple. But then, if you apply Milnor twister, Milnor twister geometrically doing connection sum. So there is a triangular exact sequence for Milnor twister.
Okay.
So that means you need to introduce triangulated category. So maybe that's what I hope someone, Bradley, that is a category, you want to become a 1 hour to go guy on the category. So you look at it. So give me a category, for example, sky category, or maybe a small category only generated by the spheres. How to get the triangular categories by adding Milnor twister. And then I think that by looking the sky-side category, which is like a sphere, and all possible Milnor twister applied to like a sphere, and then there is a triangular structure, triangulation. So that okay. So I will get back to a few more days. So usually the thesis, it'll be 2 weeks or 4 weeks to get the feedback. I'll try. I almost halfway. So I'm quite detailed. But some of these bigger diagrams in my head is very hard to go through. So
do you mean halfway through that last chapter, or do you mean halfway through the
halfway through that last chapter? Yeah, last chapter. I will send you the comment soon.
Yeah, that'd be. Yeah. Okay.
So you can still, maybe you can do something else for a few days and come back and read again.
Yeah, I've been just starting to discover some like gauge theory stuff, just having like just a playful read at the moment. But yeah, if there's anything else you want me to read, feel free to send it through at the moment.
I was thinking, I was thinking the Sinad, she's not coming to this week. And she said he's working on geometry implementation theorem. Maybe over there, they also have some category, some triangular category or something.
I can probably do it, but I've never handled those categories. Never done anything on those categories before, but I guess that's the way you learn.
Maybe we can talk more. Probably the Kingston will have another 1 or 2, a few more lectures before we come to the triangulated structure, and then we study the triangulated category. But the moment Milnor twister, next time on Milnor twist is more like a Lagrangian connection sum. Maybe I mentioned before. Suppose you have 2 Lagrangian, they meet at the one transversal points, and you do connection sum. So you get a third Lagrangian, which is virtually like a union of these 2 Lagrangian. But you at the intersection, you make it smooth. Then suppose you have another Lagrangian, meet the first one and the second one. Intersection points. Suppose intersection points is not at the like you don't have triple intersection. And then if you look at intersection points of these 2 Lagrangian, will be the union of these intersection points will be the intersection points for the conditional sum. Right? So virtually, you can intuitively think that you have a chain complex. You have L1, L2, and L3. You have chain complex L1, L3, and L2, L3. And this intersection is same thing as the connection sum of L1, L2 intersecting L3. So you can roughly thinking the chain complex, the direct sum of the 2. And then you make sure that the bundle operator preserve. You have whenever you have a chain complex and have short sequence, I give you a long exact sequence.
Then where's the Milnor twist?
I mean, the Milnor twist is connection sum. Because you suppose you have a mid circle, the 0 section circles. You have another curve, and then you apply the connecting sum in this case. Collect sum, you look at intersection. Maybe I can draw here. Okay, so suppose we have, so here is the picture, and then we have this Lagrangian sphere, which is here is S1. And then you have another Lagrangian, maybe L, and then we think with this the using top Lagrangian, the Dung twister for S1 applied to L. This is after Hamiltonian homotopy, essentially is the connecting sum of L with this. So what you do, you we cut an interval here, we cut an interval here, and then because it's a cut ball, right? So it's a one-dimensional cut ball, and then the boundary have 2 points. The connecting sum is by drawing this dependent orientation. If I do the orientation like this, and then I do this, the connecting sum, you have a new Lagrangian, which is like this. So, and this is a connecting sum. And this actually is a Dung twister.
Why after then twist the Lagrangian breaks?
It's not breaks. It's become it's okay. Here we have. Let's do this one. Here I have one Lagrangian, which is this one. And I have another Lagrangian. This L. And this is maybe this L0. This is L1. And then Lagrangian Dung twist essentially. This is after some perturbation. The same thing as the connecting sum. Connecting sum, this connecting sum at the point say Q. The connecting sum is you cut a ball and join the boundary. So what does this look like? So this one, if you have something which is okay. So now this, and then, so this is the connecting sum. So I cut the ball, and then, so this is the course. So essentially, the other way, we have a course here, and you replace this by this.
Oh, I think I get what you mean. I think I get what you mean. So you start with the L1 and then you do the Dung twist.
Yeah, starting with.
Okay.
To do the Dung twist, and then next time maybe you want to talk about Dung twist. Dung twist. So Dung twist is something is only in the neighborhood in the zero section. So here everything is same before. It's only happening like this. And then you want to do that. So if you want to look at the image, in fact this is apply the Hamiltonian isotopy like up. So usually, to be precise, you have maybe I cut it. Okay, here our zero section. So you look at the Hamiltonian vector fields. Okay, here is the cotangent, maybe cotangent model of Sn or S1, and then you have a function. And this function, you have a point x, and then you have a cotangent vector. And then you have a metric. The round metric, for example. And then you have this law of this. Okay, so what's this? So that's absolute value. So you suppose, so our Hamiltonian function, so x and c is just absolute value of c, just one dimensional. Then what is Hamiltonian vector fields? The sympathetic form is dx raised to c. And then you calculate this. Actually, you better write this as the c square and then square root. So then you have in the x direction, you take the right. So in the partial derivative in the c. So then you have inverse, because the derivative of this will be c square and then minus a half, and then the 2 c. So there is half in front because there is half here, right? So okay, then this is Hamiltonian vector fields. So this is the Hamiltonian vector fields. Oh, sorry, there's cosec, because the cosec square, you have two cosec here. So that is Hamiltonian vector fields. And this Hamiltonian vector field is unital, because if you look at the norm of these Hamiltonian vector fields, so this is, right, so this, because of this, is a unit vector. Is a unit vector. Is a unit vector. So
this SH you get from the contraction of the form? Oh, okay.
So you have a Hamiltonian vector fields contraction with the symplectic form.
And then DH.
Either DH or minus DH. And then, so here, but depend on cosec. If I have orientation, if I do the orientation like this, it's positive and negative here, and then this is the orientation, and then the unit vector is the horizontal. Each point, suppose here of x cosec, and the tangent vector is horizontal, because this is our, these are x coordinates is on S1, and cosec is the tangent direction. So it is the unit vector, is the rotation. But if you go this way, going other way, because it's minus each points, because it's elective, right? They are sign. And then you look at the effect. Look at so going. So if you look at the image, so okay, so here is our cylinder. And here is our zero section. And our this, suppose our vector fields is constant, like try to be constant. So the vector will be 0. So then there's no, the flow is the identity. And then here you have tangent vector. And then maybe here, okay, here is also constant. And then this one is going this way. So you end up, you rotate it. So maybe you apply rotation, x pi t. The pi, maybe you want to pi. And then I want to some function. This function rho, and the rho is depend on the x. And here there is one dimensional. So maybe here is our x. And rho is something like this. Okay, so this is rho or cosec. Maybe I put not some t here. And so t actually maybe t is the norm of the cosec. When here like let's say this is cosec is 1, here cosec is minus 1. So we are looking the cotangent moment S1, so it's S1 cross R. And then maybe the derivatives. Maybe I want the derivative of this, so that is 0. And then it's when we rotate it, so you have vector field like this, depending on size. So you're going to look at this. But this one we're going to other way. So it's rotated to this. So let's suppose this is our t is pi, reach to these points. So now I have a different more. I have so this is the flow of this particular time, and then this is become this, and then this is become this, and this. Remember that this flow is not well defined at cosec 0, because here if cosec is 0, the vector fields, well, these are vector fields, right? Here is our vector field. So cosec cannot be 0. So this vector field is not defined on the 0 section. But when we look at the points at the pi, with vector fields, this flow is this point to these points. So then I can define then twister, which is originally, so maybe I write this one. So originally our flow, which is defined, say pi, is defined only on the cotangent moment S1, remove zero section because the vector field is not defined on zero section. But after you apply the pi, is getting closer to this is the point antipode points. So actually, we can say that these vector fields apply with the flow pi and with c. When c getting to zero, this is the antipode points. Antipode points. So now, this is c is not zero. Then I can so this is tau x c. It define this. Okay, sorry. I mean. So now we define den twister. And we do define den twister, which is because it's not zero. I apply some this. I apply these vector fields, and then this is applied to this. And then I make sure that when t getting close zero, this will be limit will be 1. Maybe it's okay. Maybe this is our maybe not derivatives. It's just a rule function. Okay, maybe just rule function. Just okay. So when t getting smaller and smaller, this is 1. Sorry, this is 1. So when c is smaller, c is small, and this is 1, and then this and c is very small, so the antipode points. So c is 0, then they are just mapped to x. This is because it's limit. So this is the limit, and it's 0. So now, and when c is greater than 1, rho c is 0. So that means time 0 is constant. So this is constant. Right? So I apply this function, starting with this function, which is this function. Then I calculate the Hamiltonian vector fields, and the Hamiltonian vector, the unit vector, not defined on zero section. On the top is going this way, on the below is going the other way. And then I use this cutoff function such that one away from this 1, this is 0. There's no vector fields, so it's constant identity. And away from this is identity. And then when c getting closer to the 0, then I make that is pi. I just like take this, and then that is antipode map. So this is a den twister. And this den twister is well defined. So you can think that the support of this den twister. So that is the point x, where x is not equal to tau x. And we know that this is only in the neighborhood, in the disk, maybe disk bundle of the cotangent. And away from the disk bundle is identity. So now we have a symplectic, and we have Lagrangian. I mean, actually, this is Sm. And then you have normal bundle, and away from this disk bundle, which is this is identity, and over the 0 section, which is kind of antipodal map. So this is antipodal map. Outside, this is identity. And along the fiber, by this example, we apply the twist. So actually, this is before, like that den twister, which is I think defined by Den many times ago, which is for this example. Now we have using Hamiltonian vector fields and generate a flow. And this is flow which has compact support just along the 0 section. So you have the sphere which is Lagrangian sphere. So this is a Lagrangian sphere. The neighborhood is cotangent bundle. And the cotangent bundle, we apply that to Hamiltonian vector fields. and we apply the flow to the Hamilton vector fields. And then we try to, using cutoff function, so that these Hamiltonian vector fields, which is compact supported, away from this neighborhood is zero, the vector 0, the flow is identity. And then near the getting closer, we take the time pi flow. The time pi flow, which is mapping the points to the antipode points in a way. Okay, someone. Okay, so someone.
So there are dentists on higher dimension sphere. So Sn cross R.
Yeah.
I never learned that. I
Yeah.
also learned that dentist on torus S1 cross S1. But so
Yeah.
higher dimension is just
Similar, I think.
okay.
They don't really write down the formula, but they just say.
Okay.
But this dentist, do you think is on the whole fiber or every fiber, or how? Because single fiber is like what Brian said, but how to think of the whole fiber?
Probably we can close the meeting.
Brian, this dentist is acting on one single fiber or the whole fiber?
Because this is like a compact supported, you can always extend it away from that. If you need, I mean, it depends on here. I mean, if you go back, it's like onion sphere. Oh, sorry, it's different file. So if you go back, okay. It doesn't matter as long as you have a Lagrangian sphere, you can do dentist. Right. So if I take so those Lagrangian spheres.
But they are zero section from different fiber.
But now you have, okay. So in your example, so here maybe we'll look at the dentist for Lefschetz fibration. So this fiber is fixed. So we fix a Milnor fiber.
Okay, fix a Milnor fiber.
For fixed Milnor fiber, and as actually the material that observed, you need a Lefschetz fibration on the Milnor fiber. So here is a Lefschetz fibration from Milnor fiber. And then of course we have the Lefschetz fiber, right? So Lefschetz fiber, which is a sphere, which is the dimension. So Lefschetz fiber is if this is dimension dimension 2m, and then here is dimension 2. So the fiber would be, so each point, so the Lefschetz fiber will be dimension 2m minus 2. And then over there we have the vanishing cycles. So here is the vanishing cycles, which is dimension m minus 1. And then we joined by, so with the Lefschetz symbol, we use the generic fiber, and then we have a path, connecting two points. We have a vanishing cycle in the middle, and then we have this Lefschetz, which is like a Lefschetz symbol, which is a ball. And this, again, is a sphere. Our dimension n. It's not a vanishing sphere, but it's a Lagrangian sphere. So we can so now, so what is this is the general philosophy. So suppose we have E, and together with Lefschetz fibration, so this is Lefschetz fibration, and then we also have fiber. Okay, so we have, so suppose we have Lefschetz fibration, and in this case, okay, so here we also have Lefschetz fibration for some points, say x0. So this is a regular fiber. This is two-dimension mesh. And here we have vanishing cycles. So maybe I call it vanishing cycles, so Sn minus 1. Actually, you have the same numbers of vanishing cycles. M melee, M or M plus 1, M melee, okay. And these, actually these, okay, so these are single fiber. Like, I mean, here I draw it, there's maybe something like this. Maybe, okay, so if you have here our x0, here is A0, A1, so this here critical value, AM, and then we draw this, and each of these give us okay, so here we have this, so this vanishing cycles is for this, and then okay, so maybe we denote EX0, so this is 2m minus 1. We want to look at the Fukaya category, or maybe Fukaya-Seidel category. Fukaya-Seidel category. And here we want to put these SI, these cycles here. And then we adding den twister. So we also have a group with a different den twister. I from 1 to m. And then we have another, maybe also called Fukaya category or Fukaya-Seidel category for the whole space E. And here then, like, so these are a meter, so all these, if you look at here, they are different, but we move it back to the same by choose, maybe by choose some loop, which is all these ones will be identified to this. There may be some way of to this is, I think, the vanishing cycles. So this, suppose the disk, and here we have the disk, which is, and if there are, I mean, like, so okay, so here we also have which is Lagrangian sphere, which is not the vanishing cycles. The vanishing cycles are, which is this one. So now the Lagrangian sphere, which is also labeled by 1 to m, but this now have a Lie configuration. Its intersection is only 1, right? So that's true. Yeah, this is intersection is only 1. This may have some complicated intersection because just like this one, I can have this one, and then I have this one, and then I can have some going around, and then this will be, so could have vanishing cycle. These vanishing cycles could have different, not a AM type, but here you have AM type. And then you also have a den twister for these guys. Den twister is for any Lagrangian sphere.
Yeah.
So I think that I'm not sure. I haven't really read it. The Slido Pro proved that there's a relation between these two. Maybe there's a way which is like an inclusion functor. I'm not sure. We will, because it's a seminar, we will learn this.
So actually those two spheres are different spheres.
Yeah, there's different dimensions. The Valician sphere. So this is Valician sphere is half dimension is minus. Then the AM type. So this is the AM type, which is the dimension. Like if you look at all those, actually it's coming from the equator. But this equator is in the big space. But you pull this along this middle one back to this power transport, right? If you look at so these are critical points. The critical points, and whenever you have a line from regular points to the critical points, then we have a Lagrange revolution cycles, and then we have Lefschetz symbol, and then this particular shape by choosing these intervals.
Yeah, correct.
These intervals in the middle points we have validation cycles of n-1 dimensional. Then we have a Lefschetz symbol, and this Lefschetz symbol join these two. These become Lagrangian sphere. It's not a Valician cycle. Certainly not. Maybe Valician cycle something else, but it's not a Valician cycle for this Lefschetz vibration. The Lefschetz vibration is so. But this is in any case is Lagrangian sphere. This in this category. So now in Fukaya category just too big, too many Lagrangian submanifold. So we choose the finite many. So we often call the finite generated. That's easier. In this case, it's even better because intersection is only 1 point. Because the chain complex of these Li, so suppose this is Li, Lj, this is 1 dimensional, so maybe is C or maybe Z. If I minus j is 1. If I minus j is greater than 1, and then the non-intersection point. And then because it's only 1, same as Floyer homology group. So this is in this AM type. This Lagrangian intersection homology is very simple. But when we apply the Dehn twister, we'll create many Lagrangian submanifolds. Right? We do that before. We starting with Lagrangian here and then Lagrangian here, and then they will join them together. So you can do it many times. The Dehn twister, you can keep doing twisted. So and then
so this Dehn twist picture in the Fukaya category of E is different already, right?
Yeah, Dehn twist. I mean, you have two Dehn twister, one for different dimension, but certainly there is a relation.
Oh, okay.
This is on the category. We send the object to the object. Maybe not true. I'm not sure because depend on you want the embedding. The functor should send the morphism to morphism. Morphism are the chain complex. So this is the category they will usually call the differential graded category. So they call the DG category because the chain morphism has a chain complex structure. So this will be a DG category. Actually, we know that there is even more. The higher structure actually is A infinity category. All these are infinity categories. And then we want to apply Dehn twister. Dehn twister, if Dehn twist essentially suppose have a sphere applied to L, so it's homotopy, like up to diffeomorphic or maybe in the category, actually in the Dirac category, this is essentially the connection sum. Essentially, if found at particular points.
This one is general or not?
This is general. Yeah.
General, oh, okay.
At least for one intersection points. You have two intersection points, maybe it's complicated.
Okay.
If you iterate it, you can do iterated. You're just connecting some another maybe. Maybe you have perturb it, right? You have perturb it. You're not doing the same point because it's already been using. So you because you can move. Okay, so what I mean that suppose I have like a sphere here, but then I can move it away because these are all same like in terms of because category I can use in the Hamiltonian isotopy, can move around. Suppose I have something I do dump twister here, then I can do second time at different point. So then I can do it connection from another points. Then because you can do it infinite many times. So that's why you have a braid group. You have the whole braid group act on this for category, of sinusoidal category. And in some way, the orbiter is only finite. You only starting with finite many object, and you apply the group. So in some way, of course, here we have a category which is very algebraic, but then we also have the geometry, which is symplectic geometry, and then we produce this algebraic structure. So